Hello friends, welcome back to my YouTube channel. Today I'll be talking, I will be continuing my discussion on distillation. This is part 22 of that discussion, and here I'll be continuing my discussion on McCabe-Thiele method. So since uh, in my last three videos I have started discussing McCabe-Thiele method. Till now, as far as McCabe-Thiele method is concerned, I have discussed its assumptions, the simplifying assumptions that are made in the McCabe-Thiele method. Then I have talked about what is the implication of those assumptions on the operating line for the rectifying section. Then I discussed how the operating line of the rectifying section intersects with the diagonal line. And today I will discuss what will be the equation for operating line for the stepping section due to, or how the equation will be modified due to the assumptions, simplifying assumptions made in the McCabe-Thiele method. So let us start the discussion. So again, let us revisit the assumptions. The assumptions made in McCabe-Thiele method, they are called simplifying assumptions. What are the simplifying assumptions? Let us understand. The first assumption is the heat losses from the column are negligible. Heat losses to the atmosphere, they are considered to be negligible. And due to this simplifying assumption, in any section of the column, this is true. The ratio of liquid molar flow rate to vapor molar flow rate, it remains constant. Second assumption in the method is heats of solution, they are negligible. And due to this assumption, again, the fact that the ratio of liquid molar flow rate to vapor molar flow rate is constant, it is consolidated. This adds to this fact. The ratio of liquid molar flow rate to vapor molar flow rate is constant. Again, it is strengthened. Then the third assumption is the principle of equimolar overflow and vaporization is applicable. Now, what is this principle? According to this principle, if you are talking about the rectifying section, in the rectifying section, liquid molar flow rates are same for each tray. So for example, liquid molar flow rate on tray 1, liquid molar flow rate on tray 2 is equal to liquid molar flow rate from tray 3. So L1 indicates liquid molar flow rate from tray 1, L2 indicates liquid molar flow rate from tray 2. Similarly, liquid molar flow rate from tray 3 and liquid molar flow rate from tray, nth tray. Okay, so in the rectifying section, again, vapor flow rate from each tray is same. That is G1 is equal to G2 is equal to G3 is equal to Gn. Same is the case with the stripping section. So in stripping section also, this is stripping section, you please read it as stripping section. In stripping section also, liquid and vapor molar flow rates are constant throughout the section. That is L bar 1 is equal to L bar 2 is equal to L bar 3, and that is equal to L bar m. Okay, so L bar indicates that this flow is different from the flow in rectifying section. Okay, so liquid molar flow rate will be constant throughout the stripping section, but it will not be equal to the liquid molar flow rate in the stripping section. Same is the case with vapor molar flow rate. Vapor molar flow rate is constant throughout the section, but it is not equal to the vapor molar flow rate in the rectifying section. Okay, So these are the simplifying assumptions that are made in the McCabe-Thiele method. Okay, now let us look at the tray column, the schematic of the tray column. So this is the tray column. These are few trays in the tray column. The topmost tray is the first tray or first plate, and the bottommost tray is nth plate or nth tray. That means there are capital N number of trays in this particular tray column. Feed is entering on a tray, and we call that tray as feed tray or feed plate. Then I have shown any tray, and I'm calling it as nth tray in the stripping rectifying section. And in the stripping section there is nth plate, and plate next to m plate is m+1 plate. Okay, so feed, after entering on the feed plate, it flows down to the bottom, and then it is taken out, sent to the reboiler. Heat is added at the rate of QR to create a vapor phase. This vapor phase is then admitted at the bottom of the column. The vapor phase rises through the column. It is taken out at the top. It is sent to the condenser, where heat is removed at the rate of QC to get a condensate, and then that condensate is divided into two parts. One is taken out as the distillate or the top product, and these are the flow rate, and I'll talk about it, what is D and XD. And then the other part of the condensate is sent back to the column as reflux, and then this reflux flows down and adds to the liquid, that is adds to the feed that is coming on the feed plate, and this process continues. From the reboiler we are taking out the residue or the bottom product, and it will be identified by these parameters. We will talk about this shortly. Okay. The section of the column above the feed plate is the rectifying section. Section of the column below the feed plate is the stripping section. Okay, so let us understand. Now what are the conditions? You have the feed solution that is entering on the feed plate. It is actually a binary liquid solution of two components, A and B. Out of A and B, A is the more volatile component. The meaning of A being more volatile component is A has a lower boiling point as compared to that of B, and at the same time A has more vapor pressure than that of B. Okay. Then F is the molar flow rate for feed stream. XF is mole fraction of A in the feed, that is mole fraction of more volatile component in the feed. Then if you talk about distillate or the top product, then for distillate and or the top product, D is its molar flow rate. What is molar flow rate? Molar flow rate is, for example, it could be kilomole per hour, that is moles per unit time, molar flow rate. And XD, it is mole fraction of A, that is mole fraction of more volatile component in the distillate. Okay. Then for the bottom product or the residue, you have W, which is the molar flow rate, that is moles per unit time, and XW is mole fraction of A, that is mole fraction of more volatile component in the bottom product. Then the reflux that is going back to the column, L0 is its molar flow rate, and XD is the mole fraction of A in the reflux. You can notice mole fraction of A in the distillate and mole fraction of A in reflux are the same, because over here there is simple flow division, and there is that involves no composition change. Okay. And then for the reboiler, in the reboiler you are adding heat to the liquid solution. So it is added at the rate QR. So QR is the rate of heat addition. So it would be, for example, joules per second. Then in the condenser, heat is removed from vapors. So QC represents the rate at which heat is removed, and it could be so say joules per second, the rate at which energy per unit time. That will be the unit for QR and QC. Okay. Now let us look at the stripping section. As we know, stripping section is the section below the feed plate. So here I have shown by the yellow envelope. So it covers some few trays in the stripping section. Okay, so it covers, I have considered YUM plate, the streams coming from YUM plate, and then YUM+1 plate, YUM plate, and the reboil. Okay, I have shown it separately. So now you can see YUM plate, YUM+1 plate, YUM plate, and the reboil in the stripping section. Okay. So now let us use a few notations. Again, I'm showing the stripping section: YUM plate, YUM+1 plate, YUM plate. Now what are the streams associated? Before that, let us draw the envelope for which we are going to do the analysis. So here the streams are named in this way. So for example, this stream is named as L bar. The stream has like a molar flow rate of L barium and mole fraction of A in it is XM. So this is the stream, this is the liquid stream that is coming from YUM plate, the liquid stream that is coming from YUM plate. So it is identified in this way. L barium represents its molar flow rate and XM represents mole fraction of A in it. Similarly, this liquid stream is coming from YUM+1 tray. Therefore, it will have a liquid molar flow rate of L bar YUM plus 1, and mole fraction of A in it will be XM+1. This stream, the liquid stream leaving nth plate, will be identified by L bar YUM and mole fraction of A in it will be XM. Then the same liquid stream is taken out of the column and it is sent to the reboiler. In the reboiler, QR heat is added at the rate QR, which creates vapor phase. So vapor phase leaving the reboiler is identified. The vapor flow rate for the vapor leaving the reboiler is G bar N+1. Mole fraction of A in it is YN+1. So now here you can easily understand reboiler is said to be N+1 plate, and vapor rising out of it will have vapor flow rate or molar flow rate of G bar N+1 and mole fraction of A in it will be YN+1. Okay, so after coming into the section into the column, the vapor will be leaving nth plate, and that will have molar flow rate of G bar N, mole fraction of A in it will be YN, and then this is the stream that is leaving YUM+1 plate. Therefore, its molar flow rate will be G bar YUM+1 and mole fraction of A in it will be YM+1. Why every time mole fraction of A? Because A is the more volatile component. It has a lower boiling point than B, and it has more vapor pressure than that of B. So this is the stripping section that we are going to consider. Okay, so I'm showing it once again. Now let us take the material balances. First we will take total material balance for the envelope. So I will simply draw the envelope over here for your understanding. Let the envelope be represented by this yellow rectangle. Then let us now identify the streams associated with this envelope. One is the liquid stream that is coming from mth plate, that is L bar m xm. Then you have the residue or bottom product stream that is going out, W xw. And is there anything else? Okay, there is one more stream that is going out, that is G bar. I'll show over here, G bar m plus 1, and mole fraction of A net is Y m plus 1. I'm not showing the energy stream. Okay, so as far as material streams are concerned, how many streams are there? There are these three streams. The liquid stream that is coming from mth plate, let this be 1. Then you have the vapor stream that is coming out of m plus 1 tray, and the third stream is the residue stream, and that is coming out of the input. So if you have to write the total material balance at steady state, it will be written in this way. Input is equal to output. Input is L bar m and output is G bar m plus 1 plus W. I am calling it as equation 1. So input is equal to output. Then if you write material balance for A at steady state, that is material balance for more volatile component, it will be L bar m into xm, that is equal to G bar m plus 1 into ym plus 1 plus W into xw. So that is total molar flow rate of the inlet liquid stream into fraction of A net is equal to total molar flow rate of the vapor into fraction, total molar flow rate of the residue into fraction. Okay, so that gives us, let me first erase this, that gives us so if you rearrange that equation number 2, I'm calling material balance for A at steady state as equation number 2, and if you rearrange it, you are going to get this equation. L bar m is into xm minus W into xw, that is equal to G bar m plus 1 into ym plus 1. So what I have done, I have brought this W into xw term on this side, on the left hand side. In the next stream, I'll write equation for ym plus 1. Okay, so the G bar m plus 1 can be brought on this side, and you can get this equation. Ym plus 1 is equal to L bar m upon G bar m plus 1 into xm minus W upon G bar m plus 1 into xw. Okay, now what we will use equation 1. So from equation 1, I can write equation for G bar m plus 1. How that can be done? This W can be brought on this side, and you will have L bar m minus W. So from equation 1, you have G bar m plus 1 is equal to L bar m minus W. And now we can use this equation for G bar m plus 1 in this equation. Okay. So if we do that, we get Y m plus 1 is equal to L bar m upon L bar m minus W into xm minus W upon L bar m minus W into xw. Okay, let us talk more about this equation. So we just call this equation ym plus 1 is equal to L bar m upon L bar m minus W into xm minus W upon L bar m minus W into xw. This is equation 3. And if you assume equimodal overflow and vaporization, then what will be the case? The liquid molar flow rates in the stripping section for every tray. Similarly, you can that means L bar m can be any of this liquid flow rate. It could be liquid flow rate that is coming from first plate in the stripping section, or the second plate in the stripping section, or m plate from the stripping section. Now you please remember over here 1, 2, 3, this represents I have numbered the trays in the stripping section. Are you understanding it? So this is not the first tray in the column. Over here L1 represents the first plate in the stripping section. Okay, so if you look at equation number 3, you can say you can clearly understand this equation number 3. It represents a straight line on xy plot. What is xy plot? Mole fractions of A are plotted on y-axis. Mole fractions of A in the liquid phase are plotted on x-axis. So these are equilibrium mole fractions. Every x is in equilibrium with every y. So if you are plotting such values, you will be getting the curve, that is the equilibrium curve. And this diagram is said to be the distribution diagram or the xy plot. This is the equilibrium curve. Equilibrium curve. Okay, so on this diagram, on this equilibrium curve, on this xy plot, equation number 3 is a straight line. What is the slope of this straight line? Slope is L bar m upon L bar m minus W. Slope. This is the slope of the straight line, and this is intercept made by the line on y-axis. Intercept is minus W upon L bar m minus W. So L bar m upon L bar m minus W is the slope, as I said earlier, and the intercept made by the line on the y-axis is minus W L bar m minus W into xW. So in this way we can get the equation for the operating line for the stripping section. Okay, so that was the objective for this discussion. We have got the equation for the operating line of the stripping section, and due to the assumptions of the McCabe-Thiele method, we can get this liquid flow rate is constant throughout the stripping section. So you can simply write slope will be, say, L bar upon L bar minus W. So if you represent where L bar in this case is representing liquid flow rate in the stripping section. Okay, so this is the equation. I hope you have understood the concept. If you have any doubts, you please mention that in the comment section. So this is the operating line for the stripping section. Operating line which has this slope and which has this intercept. Okay, so with this I end my discussion for today. I hope you have understood the concept. Now we know how to get the equation for operating line and what will be the effect of assumptions of McCabe-Thiele method on that equation. Thanks for watching my video. Do subscribe to my channel. Please tell your friends to subscribe to my channel. Thanks for being with me. For now, have a nice day. See you soon in my next video.